Welcome to this XACC Tech Talk. My name is Cathal McCabe. If you've previously attended one of our Tech Talks, you will see a new logo on the screen. Xilinx is now part of AMD, and we are the Adaptive and Embedded Computing Group in AMD. These Tech Talks are intended to highlight some of the applications and research related to the Adaptive Compute Clusters program. The program is a special initiative to support novel research and in adaptive compute acceleration for high-end computing. Clusters have been set up at partner universities around the world, consisting of compute nodes enabled with Alveo adaptive compute hardware. If you're a researcher working in high-end compute and related fields, we invite you to apply to join the program, and you can get remote access to these nodes, which you can use for your own research. You can find a web link to the program on the screen. You can find details on the program and also view recordings of previous Tech Talks. I'm pleased to introduce my colleague who is giving his second Tech Talk. Dr. Lucian Petrica is from the AMD AECG Research Labs in Ireland, and will talk about his work on ACCL, an open source FPGA-accelerated communication library for application scale-out.
Thank you, Cathal, for the introduction. So I'm going to talk about ACCL, which is a piece of infrastructure that we believe will help people in the future perform interesting research on application scale-out, and will also help users interested just in performing the distributed computing scale-out from one FPGA to multiple FPGAs. And hopefully during this talk, I'll explain why ACCL is potentially useful and how it achieves the benefits that we claim. So the agenda is to go a bit on the motivation of this work and why we need communication and distributed computation, and then how ACCL implements MPI collectives, which are the main mechanism for communication in distributed applications today. I'll give an overview of ACCL performance as measured on the ETH Zurich XACC, and then I will show briefly how ACCL can be used by researchers to implement their own application and to integrate with their own applications and target Alveo cards. Then I'll briefly discuss what our roadmap is and take questions. So starting first with the discussion about the motivation of why work in distributed computation is so important right now for FPGAs just as well as for GPUs. And I'm going to start with a discussion of the elephant in the room. Obviously, AI applications are the main drivers of compute and memory requirements today. And the increase in requirements from AI applications over time has been much greater than the increase in single device capability provided by Moore's law. And this is true today and will be more true in the future as Moore's law tapers off. So there is no way that we can actually keep up with modern AI applications in the data center with computation on a single device. And even if computation requirements weren't a problem, memory requirements come in, and modern AI models are so large that they cannot possibly fit into memory of a single computational node in a data center. So this is obviously a problem, and it means that we are fundamentally limited in what we can do with a single computational device or a single server. And you might say that, okay, this is limited to AI applications, but AI applications have essentially taken over data center workloads and are increasingly being integrated into high-performance computing applications such as simulations, drug discovery, and so on. So we will see these kinds of requirements apply to all workloads in the future. So obviously, single-node computation is out, and distributed computation is in, where computation is broken up across multiple accelerators and nodes. And the compute alternates on these nodes with communication rounds, which aggregate data from all of the nodes such that they can remain synchronized. And in this type of approach, the compute is equal in importance with the communication, because if you compute faster, but you don't communicate faster, then obviously you won't get application speed up because the communication becomes a bottleneck. And this has driven quite an increase in the speed of interconnects. We're now over 100 gigabit per second in most data centers, but also it's a driver of hardware design right now. And I'd give the Alveo as an example of this, because the Alveo is a clear example of how you can actually integrate both communication and computation functions into a single piece of hardware. Because with the Alveo, you have the ability to compute on the FPGA, you have attached memory, but you also have attached network, and you can do all of these three functions in a single device. So that means we have the hardware, but we have to expose it up to the programmer. And typical distributed applications require specialized communication libraries, and the de facto standard for distributed applications right now is MPI. The message passing interface standard, which is sort of a common language across all application developers. And if you want to provide some functionality that accelerates distributed computation via the communication route, then you have to integrate with MPI. So let me give a short overview of what MPI is, and then I'll get to ACCL. So MPI is a standard, a set of functions which allow you to easily perform communication between two or more nodes or ranks in MPI parlance. So here we have an example of two send-receive pairs. Rank 0 sends to 1, and rank 1 then sends to 0. And this is achieved with 2 lines of code executing on each of the 2 ranks. So this is really very compact. But in real world, the applications require many of these sends and receives in coordinated fashion to achieve communication patterns which are quite large and which achieve communication between many nodes, not just 2. So that means MPI must provide a higher level set of communication primitives, which are called collectives, that an application developer can leverage to implement their highly parallel algorithms. So these collectives, let me just give you some examples. These collectives are the basis of communication in real applications, and they can be broadcast, like I illustrated here, where a piece of data from one node gets to all of the others. It can be a scatter, where pieces of data from one node get distributed to the other nodes, or the reverse of scatter, which is gather, or a reduce function, where you essentially do a gather, but while aggregating, you also perform some operator between the pieces of data. And this can be a simple arithmetic, like addition, subtraction, multiplication, or it can be something more complicated with a global scope, like, for example, taking the maximum of a vector or something like that. So MPI really allows you to make use of these primitives with just a line of code for each. And that's the power in this approach. You don't need to know what's going on underneath. You just need to know what the API is, and the framework takes care of the rest. So just let me give you an example here with distributed inference. Let's say we have 4 nodes and we want to do distributed classification on these 4 nodes. Our images are on rank 0. We want to get them to our ranks. We perform a scatter. Then we perform inference in parallel on all of the ranks to get our classes. So now we know what the images represent. And then we want to get the results back to rank 0. And therefore, we need the gather, which we implement with MPI. And all of this can be as little as 3 lines of code, like I'll show in a few slides. So this is really a powerful mechanism to assemble distributed applications. So how does MPI work under the hood? How does it integrate with the control and the compute function? Well, let's look at a brief history of this to show what the context is and how we believe it can evolve in the future. So MPI started by providing support for CPU compute. So MPI, OpenMPI, and pitch are libraries which provide essentially compute on the CPU, but in time, MPI libraries evolved to provide the ability for GPUs to execute the compute and access the network directly. So libraries such as Nickel from NVIDIA and Rickel from AMD enable a GPU to execute MPI calls, or more likely enable the system to execute MPI calls on data residing in GPU memory. And that data is then communicated directly across the PCIe bus through the network interface out into the network. But crucially, the control still runs on the CPU. So there's no getting around the fact that you need a CPU here, and that can actually become the bottleneck. So how does it work for FPGAs? Well, we can treat FPGAs as a compute device, and then they're just like a GPU, nothing different. But additionally, FPGAs can take over the networking function. So you can have something like this, where the FPGA is both a compute device, but is also a specialized network interface card. And that means the data doesn't have to travel from the FPGA through PCIe to the network interface card. It can just go directly from FPGA into the network, and that can reduce latency significantly. But still, that's not all we can do with FPGAs. We can implement control functions on the FPGA much more efficiently than we could on the GPU, and we can take over the control function from the CPU and also perform it on the FPGA, such that we can have compute on the Alveo, on the FPGA, and then we can have all of the communication function, including its control and data movement across the network, also integrated in the FPGA. And this is the type of paradigm that we target with ACCL. And I will explain how that's implemented in the following slides. So what ACCL does is it provides a library of MPI-like collectives for FPGA. I say MPI-like because we don't implement all of the MPI library, because that's a very large library, but we implement a key set of collectives which are important to most applications. So ACCL design goals are to allow ultra-low latency communication between FPGAs using MPI-like calls. And that means we need to have control offloaded to the FPGA into a dedicated Vitis kernel, which we call the CCL offload kernel. We also need to provide support for send-receive and the most common MPI collectives, which are broadcast scatter, gather and all gather, and reduce, all reduce, and scatter reduce. We analyzed a broad set of applications, and we found that this set of 7 collectives solves most of the applications that we've looked at. So it's essentially the minimal set of collectives which you need to implement quite a wide range of applications. What we also wanted is was to integrate with popular protocol offload engines. So for example, the UDP and TCP interfaces which Xilinx and ETH Zurich respectively have provided in open source for FPGA users. So we want to make use of those. And also we want to enable automatic management of memory such that the host is not involved in this, and also provides the ability for the communication function to be called from the programmable logic itself. So far, when we talked about MPI, you always need some sort of application which initially runs on the host CPU to call the function and provide all of the orchestration on the CPU. With ACCL, we want to do everything on the FPGA and provide the ability for FPGA kernels to call directly to the library in Fabric without going across PCIe with the attached latency. So we can have a hostless invocation, and also we can have expandability via Vitis plugins. So the CCLO can attach to arbitrary Vitis kernels, which can be defined by the user and which can provide various additional functionality that ACCL doesn't provide right now. So for example, you can think about adding plugins for custom data types, for network compression, and so on. So really the scope of this is very wide. So within that approach, we implemented a mechanism where we have a very light software stack on the FPGAs, on the CPU side, which involves the user application, but also lightweight ACCL drivers in Python or C++, which sit on top of the Xilinx runtime and communicate with the FPGA. And inside of the FPGA, We have the collectives communication offload engine, the CCLO kernel that I mentioned before. That's the core of ACCL, and it implements the collectives that the user can call. The CCLO communicates with the protocol offload engine, either TCP or UDP, or in the near future, RDMA. This is also a Vitis kernel, so everything is linkable with the Vitis linker. You can optionally have user kernels that interface with ACCL, and these kernels can interface with ACCL via either off-chip or on-chip memory, so that's PLRAM, DDR, HBM, or through streaming data interfaces for actual data or for commands. So in this, we can create such a system which is linked with Vitis, and that allows a user kernel, which is kernel 1 in this diagram, to send data to the CCLO and provide a command and say, CCLO, you should do a broadcast, for example. And the CCLO will execute the broadcast with no host intervention whatsoever. So we implemented this, but let's see what sort of performance we were able to get, and some objectives here. We looked at scalability and portability, and performed all of this evaluation at the XACC at ETH Zurich, comparing against OpenMPI 4.1 over 100 gig TCP. We looked at a couple of scenarios here, so host-to-host and FPGA-to-FPGA. They're illustrated here. So in the host-to-host scenario, the initial and the source and destination buffers are in host memory. In the FPGA-to-FPGA scenario, the host and destination buffers are in FPGA memory. So that means OpenMPI is really very good at doing host-to-host communication, because OpenMPI will execute on the CPUs and will move data naturally from host memory to host memory via the Mellanox card. And ACCL naturally performs FPGA to FPGA communication, because it can take a piece of data from FPGA memory, directly move it across the network ports of the Alveo into a different Alveo and provide the result in that Alveo's memory. So really, these two frameworks are targeted to different scenarios, but we will show that sometimes ACCL is as good or better than OpenMPI, even for the host-to-host scenario. So let's look at actual results. This is send and receive, throughput versus message size. And in this case, ACCL executes FPGA to FPGA, and OpenMPI executes host-to-host. So what we can see here is that the performance on the two cards that were available on the XACC at the time of testing is similar. So the design is portable. And really, the only difference between these two designs is the linking script. All of the rest of the hardware is identical, just the linking script is different. And if you want to port over ACCL to a different card that you might be interested in that supports Vitis, then all you need to do is write the linker script, and that should be everything. Now, compared to OpenMPI, we can see that ACCL achieves higher throughput than OpenMPI for all messages larger than 1 megabyte. So that means we have sort of underperformance compared to OpenMPI before that, so in the range of a few kilobytes to a few hundred kilobytes. And then from 1 megabyte onwards, ACCL is the clear winner in this comparison. And this can be explained by some overheads which are incurred through execution via XRT. Let me just give you also an overview of collective performance. So I'll start with the scatter, not because it's important, it's the most important collective, but it just makes it easy to illustrate some trends here. We see the same sort of curves as in the send receive, but maybe a little bit more pronounced here, which is that for small message sizes, OpenMPI outperforms ACCL. Lower is better here, and keep in mind the y-axis is logarithmic. So for small messages, definitely OpenMPI is the better solution. And that's really because of the fact that to execute ACCL, we have to go through the FPGA launch infrastructure, that means XRT. And currently, one call to XRT incurs around 50 microseconds of overhead. And that means we have to add that to any real transmission latencies that we might see for the actual message. So that means there's quite a bit of a floor to latency for small messages. However, for large messages, there is a performance advantage, just like for the send and receive. And that means that the key takeaways here are that if your application tolerates large messages, then you should port over to ACCL. And also, if your application needs small messages, then you might be able to make use of ACCL after we provide the functionality to control ACCL directly from the PL, and that's a feature that will be available in the near future. So let me show you the rest of the collectives. The story is pretty much the same for all of the other ones. I will just insist a little bit on the all reduce to the bottom right here. So what you see in the all reduce is that even for the H2H scenario, which is normally advantageous for OpenMPI, ACCL is still faster than OpenMPI even with H2H. And that's not only because we do all of the orchestration of the collective on the FPGA, but also critically we do the arithmetic corresponding to the all reduce on the FPGA as well. So that means instead of having to launch a piece of code which will do some arithmetic on the CPU or on the GPU, we can just do it on the FPGA as the data is going out into the network. So this sort of streaming computation lets us get that good performance for the all reduce. Looking at scalability, we evaluated 3 up to 8 ranks with all reduce with large message sizes. We looked at 100 runs. We're showing here average and the range. And what we're really looking at is to see how latency evolves. And what you're hoping to see is essentially the green line that represents ACCL performance. Going from 3 to 8 nodes, you should see slow and steady increase in latency, like you see for ACCL. Instead, with OpenMPI, you see quite large changes in performance when you go from 4 to 5 to 6 to 8 nodes, and you can definitely see that the OpenMPI algorithms are sort of tuned to power of 2 numbers of nodes, and not so much for more exotic numbers of nodes such as 5 or 6. And also looking at the jitter, there's quite a large range of values that OpenMPI latencies take during those 100 runs, whereas with ACCL, there's really no variability in the execution. It's always very predictable how much the collective will take. So that can be an advantage if your application is sensitive to jitter. Looking at resource consumption, here we have a table of LUTs and DSPs and block RAMs for all of the components corresponding to the ACCL ecosystem. So we're excluding user kernels here and just looking at the parts of the stack which correspond to communication functionality. And we can see that the CCLO itself is about 15% of the LUTs on U250. It's not that large, I would say, it quite easily synthesizes to 250 megahertz. What is large instead is the TCP protocol offload engine. I would say that the CCLO plus the TCP, if you want to have ACCL over TCP, you really have to dedicate one SLR of your board, either the U250 or the U280, just for ACCL. If you can tolerate, if your fabric is lossless or your probability of loss is very, very small, you can look at UDP, which is much more compact. With UDP, we can't do send and receive arbitrarily because there will be conflicts on the fan-in of messages. But we can do all of the collectives, and the overhead is much less. Take from this what you will, but I would say that for most applications, this overhead may be tolerable if you are able to get lower latency for communication. So let me show you quickly how one user would interact with ACCL and how you actually use it in practice. So You clone the ACCL repo. Everything is open source that I described here, and this is in active development. In parallel, you build and verify your distributed application, and we provide handy emulators and simulators for ACCL, so you can essentially prototype your application against ACCL without actually building any hardware, which we believe is super useful and very, very fast compared to actual hardware development. And then once you're done, you can build the appropriate CCL kernel and link with Vitis against your own kernels and deploy to Alveo. So everything is very smooth. Now, to give an example of how the host code would look like, just returning to this distributed inference, as I said, with MPI for Pi and Python, it's 3 lines of code. And with ACCL, as you can see here, you can get it in 3 lines of code if you want to do it quickly. Or if you want to do it in an optimized fashion, you need an extra line of code and a little bit of extra magic sauce here. The magic sauce is not that complicated. We have the ability to run ACCL calls asynchronously and to do call chaining in the FPGA with DRT to limit the latency of scheduling these calls one after the other. So you can really get a lot of performance with very little code using ACCL, and it's very similar to the starting code in MPI for Pi. So hopefully this will be very accessible to people who have experience with MPI, but not with FPGA that much. So just to give a summary, we provide here a piece of infrastructure which exposes collectives similar to the collectives in MPI that work on Alveo and 100 gigabit per second. Everything is accelerated in FPGA and is Vitis compatible, so it should be easily extensible, and it's open source, so you can modify it if you'd like. We provide an emulator and simulator for rapid prototyping and in-depth debugging and performance exploration, and we hope that this can be a useful platform for people to experiment with distributed applications on Alveo. In the near future, we will release deployment packages for XACC this spring, and we're working on HLS bindings to reduce the overheads for calling ACCL on small messages. When we're also working on application framework integrations in ML and HPC. So for example, I have an intern currently which is working on an integration with PyTorch. So we hope that this will make it even easier for people to make use of ACCL in their own projects. So with this, I just want to add that this is a super active topic of research in our laboratory, and collaborations are welcome. You can apply for internships with us, or you can collaborate with us through open source. We welcome pull requests or feature suggestions or any sort of feedback on how we can make this piece of infrastructure more useful to the FPGA users. So with that, thank you very much, and I'll take your questions.